Welcome back to mathkernel, and welcome to the finale of the orthogonality chapter. You've built orthonormal bases. You've earned them from any basis with Gram-Schmidt. You've met the orthogonal complement. Today it all pays off in one picture. A point sitting off to the side of a subspace, and the single closest point inside it, the foot of a dropped perpendicular. We turn that picture into a theorem, and the theorem into a formula. Everything today rests on one tiny definition. A scalar product gives you a norm, a length, and the moment you have length, you have distance. The distance between 2 points is just the length of the vector between them. D of AB is the norm of a minus B.
So distance isn't a new gadget, it's the length of the arrow from one point to the other.
Exactly, and that inheritance makes it a genuine metric almost for free. It's never negative, and it's zero only when the 2 points coincide. That's the norm being positive definite. It's symmetric because minus a vector has the same length as the vector, so A to B and B to A measure the same.
And the triangle inequality. That's the one that usually needs real work.
Here it's a one-liner, because the norm already satisfies its own triangle inequality, the one we pulled out of Cauchy-Schwarz back in Chapter 1. Apply it to A minus B plus B minus C, and the metric version drops right out. No new machinery. So, a scalar product quietly comes with a distance, and it's automatically a metric. That's the stage. Now the real question. Now the question the whole chapter has been building toward. You have a subspace U, a line, a plane, and a point X sitting off to the side of it. Which point of U is closest to X?
On the board, that's the blue line U, and X floating above it. My eye says, drop straight down onto the line. The foot of that perpendicular looks closest.
Your eye is exactly right, and pinning down Y is the job. First, the distance from X to the whole subspace is the infimum, the greatest lower bound, of the distances to every single point of U. That's a number. It's the best you could ever do.
Hold on, an infimum is just a lower bound. Why should any actual point P in U hit it? Plenty of infimums are never reached.
Sharp objection, and in full generality you're right. For a weird set, the closest point can fail to exist. But for a finite-dimensional subspace, it always exists. That point is called the best approximation of X in U, and it's the foot of the perpendicular, the green point P.
So P is the shadow of X on U, and any other point Q on the line, the helper point, is farther away.
That's the claim we have to earn. Two things to prove: that this closest point is unique, and a clean test for recognizing it. Both are coming. So the central object is the best approximation, the single point of U nearest X. Everything now is uniqueness and a characterization. Before we find the closest point, let's prove there can only be one. Suppose there were two, P1 and P2, both sitting at the minimal distance delta from X. We'll show they're forced to be the same point.
On the board, both P1 and P2 are exactly distance delta from X. The two dashed arrows are equal length.
Right. Now here's the move. Take their midpoint M, the average of the two. Because U is a subspace, closed under sums and scaling, that midpoint is still inside U. So its distance from X is at least delta, like everything in U.
But geometrically, the midpoint looks closer to X than either endpoint. Doesn't that already contradict it?
That's precisely the tension, and the parallelogram identity turns your intuition into an equation. Set U equal to X minus P1, V equal to X minus P2. Then U plus V is twice X minus M, and U minus V is P2 minus P1. Feed those into the identity.
So the two things I care about, the midpoint's distance and the gap between P1 and P2, end up in the same equation.
And it pins them together. 4 times the midpoint distance squared, plus the gap squared, equals 4 delta squared. But the midpoint distance is at least delta, so its term is already the whole right side, leaving the gap squared at most 0. A length can't be negative, so the gap is 0. The points coincide.
So the very existence of a second closest point manufactures a strictly closer midpoint, unless they were never 2 points to begin with. That's genuinely slick.
One elegant identity does it. If a closest point exists, it is unique, no room for a tie. Here is the heart of the whole video, the characterization theorem. A point P in U is the closest point to X if and only if the error, P minus X, is perpendicular to all of U. Closest, exactly when the mistake you're left with points straight out of the subspace.
So the test isn't about measuring distances at all. It's just, does the leftover arrow make a right angle with you?
That's the whole beauty of it. 2 directions to prove. Start with the easy, satisfying one, the arrow. Assume the error is perpendicular to U, and take any other point Q in U. Split X minus Q into the error X minus P plus P minus Q, which lies inside U.
And since the error is perpendicular to everything in U, it's perpendicular to that second piece specifically.
Exactly. So those 2 pieces are the legs of a right angle, and Pythagoras applies. The distance to Q squared equals the error squared plus the P to Q squared. That extra term is never negative, so Q is never closer than P. Done, P wins. That's the reverse direction.
Now the other way, if P happens to be closest, why must the error be perpendicular?
Watch a little calculus sneak into linear algebra. Pick any direction U in U and slide. QT equals P plus TU, a whole line of candidates through P. Measure the squared distance as a function of T. Expand with bilinearity and you get a parabola, a quadratic in T with a positive leading coefficient.
And P being closest means that parabola bottoms out exactly at T equals 0.
So its derivative at 0 must vanish. That derivative is minus 2 times the scalar product of U with the error. Set it to 0 and the scalar product is 0 for every direction U in U. The error is perpendicular to U. Both arrows proved. So closest and perpendicular are the same statement. Pythagoras one way, a bottoming out parabola the other. Now the theorem is beautiful, but you want the closest point in your hands, computed. And here's the payoff, you already have the formula. Remember the Fourier formula from a few videos back? Take an orthonormal basis of U and some x dotted with each basis vector, times that vector.
Wait, back then that formula just rebuilt a vector from its coordinates. Now you're pointing it at a subspace that doesn't even contain x.
That's the twist. Feed a vector that lives outside U into the same machine, using only an ONB of U, and it can't reproduce x. It produces the projection, pi U of x. Same arithmetic, doing geometric work now. Instead of decomposing, it's dropping the perpendicular.
Bold claim. Prove that this pi U of x really is the closest point, not just some plausible-looking vector.
By the theorem, I only need one thing, the error perpendicular to U. And to check perpendicular to all of U, it's enough to check against each basis vector. Bj with x minus the projection. Bilinearity spreads it out, and orthonormality, the Kronecker delta, kills every term except the matching one.
So it collapses to x.bj minus x.bj.
Which is 0 for every basis vector. So the error is perpendicular to U, and the characterization theorem instantly upgrades that to pi U of x is the best approximation. The formula you learned for coordinates was quietly the projection formula all along. So the Fourier formula's real job is revealed. Given an ONB, it hands you the closest point, no minimizing required. Let's compute one all the way through. In 3 dimensions, take U to be the xy plane, but hand it to yourself through a tilted orthonormal basis, B1 and B2, each a 45-degree unit vector inside the plane, and a point x equals 2, 3, 4, sitting 4 units above it.
Why the tilted basis? The xy plane has the obvious basis. This feels like you're making it harder on purpose.
On purpose? Yes, to show the formula doesn't care which ONB you pick. It should still find the same closest point. So, two coordinates, each a single scalar product. X dotted with B1 is 5 over root 2. X dotted with B2 is minus 1 over root 2.
And then I just stack those two pieces to build P.
Assemble it. 5 over root 2 times B1 minus 1 over root 2 times B2. The root 2's cancel against the 1's in the basis, and it lands exactly on 2, 3, 0. Clean integers from a deliberately messy-looking basis.
2, 3, 0, that's just X with the Z part knocked off. So the tilt inside the plane genuinely didn't matter.
Exactly the point. The projection depends on the subspace, never on which orthonormal basis you describe it with. And the distance is the leftover perpendicular error, 004, length exactly 4. That's d of x to you. Coordinates, projection, distance, all from scalar products, and the answer is basis independent, as it must be. That's distance and best approximation. The closest point in a subspace is the foot of the perpendicular, and the Fourier formula computes it. And with that, the whole orthogonality arc closes. An orthonormal basis gave us effortless coordinates. Gram-Schmidt earned 1 from any basis. The orthogonal complements split the space in 2, and today projection and best approximation cashed all of it out as one clean picture, dropping a perpendicular. So orthogonality, start to finish, was really one idea. Right angles turn hard problems into easy ones. Next chapter we let those right angles move, isometries and diagonalization, where the maps that preserve length take center stage. Thanks for watching.